Okay, let's get started. I'd like to go back one page behind. So we went through this last time, last lecture. So this is buck converter in the steady state. First of all, we assume this our voltage is this one, and this is ripple free. Means this is purely DC. So it's called. Your assumption you are using here is small ripple approximation. So you're assuming this is entirely DC quantity. Small ripple approximation. Okay. And during on time period when this switch, this is gonna be MOSFET. Probably is turned on, this diode is turned off because of this voltage is reverse biasing this diode. So current passes this one. During this time, this voltage is Vs, and at the initial state, voltage here is 0. So the energy is pumping into the inductor. That is the on-time period. This is the equivalent sub-circuit of on-time period. So this circuit reduced to this simpler one during the on-time period. It's called on-time sub-circuit. So during the off-time period, so this inductor wants to keep its continuity. So it's turning on this diode, and current is flowing like this. Then there is some voltage, and this voltage becomes negative. That means the energy is going this direction. So energy is dumping to this load resistor and this capacitor as well. And during that period, which is this one, 1 minus dTs, so you have this circuit, equivalent circuit, valid during this time period is called off-time sub-circuit. So this diode with red color, diode in red means the diode is turned on. So it behaves as a short circuit. And this is switch drive signal. So this on-time period, off-time period. Of course, this is the switching period TS. Okay. During on-time period, the VL, voltage across this inductor, is Vs divided by VO. This is the DC based on the small ripple approximation. So you have this flat DC, and during this time, this voltage is negative of this voltage because the polarity, this one and this one is opposite. So you have this minus voltage, and repeating this. So the volt-second balance condition about the inductor voltage, that means area of this rectangle is the same as the area of this rectangle. So with this, we established one equation, and this will be converted this to provide the voltage gain expression. Of course, this is the D. We confirm this in time domain analysis and frequency domain analysis as well. So this is true because D is some number between 0 and 1. So voltage gain is something between 0 and 1. And this condition, this is the volt-second balance condition. So that means this area during the on-time period is balanced to the area of off-time period. Otherwise, you're in trouble. Okay? All the PWM converter you are discussing in your class, in your research, there is a way of meeting this. Otherwise, your circuit won't work. Okay? You have some disaster, some bad thing will happen. So practical circuit should always meet this volt-second balance condition. And as I said, the average value of inductor current should be same as load current, which is this. And during, so this is the average value of inductor current. And during on-time period where this voltage positive and constant, okay, this voltage constant, then this inductor current is increasing linearly. Equation of that is this, okay. So this equation, this is true when the inductor voltage is not varying, just DC. Then If that value is positive, it increases, and during uptime period, this is minus VO divided by R, that is slope. Then it decreases linearly. So you have this kind of waveforms, and this is average value, and variation of inductor current del IL is on-time slope and on-time period. Multiplication of those two terms should be same as this is uptime period, uptime slope and uptime period. Okay, that is the meaning of periodic steady state. So this value should be same as this one, and this value should be same as this one. So from this, you can easily calculate the peak value and value of this maximum value, minimum value, all right? And this is the circuit diagram of buck converter. I did draw previous one to illustrate this waveform with this, okay? This IQ is a switch current, ID is diode current, this is IL is inductor current. So inductor current is IQ plus ID, okay? In different time, for the on-time period, IL is IQ, or IQ is same as IL. So during this on-time period, so this current is same as this. So there is 0 is here. This is just the mean value of this. This is 0, okay? And during uptime period, this portion of inductor current is same as the diode current. So again, this is 0. So this is average value of these waveforms. This is average value of this pulsating waveforms. Okay. Average value of this is IL is given here. Then the average value of this IQ is D times IL. So IL is average value of entire period, and during only DTS, this IQ copies this IL. So we have weighting factor D here. Likewise, during this period, the average value of this diode current is IL times, this is the weighting factor, 1 minus D. Okay, this is obvious, all right? And IC is this capacitor current. So IL is this one, IL is this one. So it has this DC component, and it has also it has AC component. The easiest way of finding AC component of this is triangular waveforms. You just know this triangular waveforms by this amount. Okay, push down the entire waveforms by this average value. Then what you are having is this one, this. So variation here is average value of this. Then this is AC component. Okay, so this is combination of this DC component and this triangular waveforms AC component. Okay, average value of this is 0, should be 0, because this one is symmetrical. So that means the meaning of AC component. Okay, so think about two components separately. So DC component of this inductor current, it cannot go this because it presents infinity reactance at DC. So all the DC current is passing through this. All right. How about AC current? This AC component has two passes. It can go either this way or this way. But usually you are using large capacitor to reduce the ripple component of our voltage. That case, reactance of this at the switching frequency is much smaller than this resistance. So almost 90 or almost all of this AC component will pass through this one. Okay, that is our desire. Okay, so ideally entire AC is, we assume entire AC component is passing through this capacitor, and only DC component is passing through this load resistor. That is another assumption. So, and this voltage is VO, our voltage, and this is DC current is VO divided by R. Okay, so this is VCT, voltage across the capacitor, which is the same as our voltage in partially, not entirely. Then this VCT also contains this DC component plus VAC component. Okay, and this one we are assuming this now. Previously we are assuming this is 0. So small approximation indicate this is 0, and this is VO. So this is then VO plus VAC AC component of this our voltage, which is ripple voltage, which is very small compared to the DC value. Okay, but somehow we want to evaluate this one. Okay, that is shown here. So from this you construct this. This is what? Capacitor current. So the charge balance means the area of this part. This positive part should be same as area of negative part. Okay. Otherwise, the capacitor voltage will increase eventually, and the capacitor will explode. All right. To avoid that tragic situation, the circuit is designed to meet this condition. So this is IC is IL minus large IL. So this inductor current minus DC component of inductor current. So this is AC part of inductor current. We sketched that here. Okay. So this AC current is passing through this capacitor. Then you have equation. Okay. So ICT is constant. That comes out here. But this is this time function. Then we need this integration. Okay. So when this is positive, this voltage is increasing. This is the minimum value of this VAC, and during this period of time in which this IC is positive, it is increasing. This is not exactly sinusoidal. I don't know. I just sketched it. Okay. And when this is negative, it goes down. Okay. And this is this peak to peak value of VAC is important. This is del VAC. Okay. What we want to know is just this one. You are not interested in equation of this. You are not interested in the exact waveform of this either. Okay. What we are interested in is just this value. This is the magnitude of ripple. Okay. So don't try to calculate this, or don't try to draw exact waveform of this. That is the unnecessary. You just catch this peak to peak value, which represents the AC component contained in DC. So if you find out DC, then your actual waveform is this DC, and it has AC component on top of this DC value. Okay, that is the way of reconstructing the ripple component from the simplified analysis, assuming the output voltage is DC. Okay, so you can you evaluate this later. We will have some formula, very simple formula to evaluate this. We have some example here. This is the buck converter example. All right. So inductor, capacitor, and load resistor, and the switching period is 20 microsecond, and the D is 1/4. Then our voltage becomes, Curie ratio is 0.25. I'm sorry. Times 16 is 4 volt, and average value of inductor current, which is load current, is VO divided by R is 4M. Okay, so this is our prediction. This is a theoretical analysis of this converter. So there was result of that analysis of voltage and the maximum of this inductor voltage, minimum of this inductor voltage, and the average value of inductor current, and the del IL, IL max, IL min, everything is calculated based on this analysis and previous piecewise linear analysis. Okay, in previous analysis we used piecewise linear analysis and the small ripple approximation and both second balance condition on inductor and second balance condition. For the capacitor, maybe somehow we use the Ohm's law, something like that. Very simple, extremely simple. This is the result of the piece by simulation. So this is the same as this prediction. This is the maximum value of the VL. And this is the waveform of uptime period. Area of this thing should be the same. So it has the same value. And this average is 4M, okay? And during the on-time period, this current is passing through diode, and this off-time current is passing through this, this one is passing through the switch, and this part is passing through diode. So, okay? So everything is ideal. And next slide shows the estimation of our voltage ripple, okay? We ignored the output voltage ripple and we assumed output is a pure DC, and that is not true. Okay, so this is IL. This represents the variation, fluctuation of IL, and the average value is somewhere here. And you bring down this by that amount, then you have this. Okay, so you have this structure, and the area of this triangle is the same as area of this. That means this height, this small height is half to del IL, and the duration of this should be the same as this, and this one should be same as this. Okay. Otherwise, we don't have the zero value as its average. Okay. To have perfect balance at zero, this should be satisfied. That means the period from here, there, it start crossing this 0 ampere line, and again crossing 0 ampere line should be half to switching period. Okay. From this geometrical construction, we conclude that this is what? This is TS. This is one switching period TS, and this is half to switching period. When this current is positive, this voltage is increasing, and this current is negative, it decreases. Okay, so we use this equation because this is time varying. Okay, and what you want to know is this one, magnitude of this peak value and this bottom value. Okay, then we evaluate this. Okay, because this 1/c is coming here. And this is indefinite integration, and this is a definite integration. We integrate only from T1 to T2. During that period of time, this ripple voltage will be increased by this amount. Okay, so this is integration. This definite integration is same as the evaluating the area of this shaded triangle. You learn this in your high school or middle school. Okay, so this is the equation, and this area can be evaluated from this geometry of this triangle. So you have 1/c. Because of triangle, you have 1 divided by 2, and this is the height of this triangle, and this is the width of this triangle, and this del IL as given by this is the uptime slope and uptime period. Okay. You can use this on-time slope and on-time period, but it's better to use this out voltage if possible. The reason for that is later on you will be regulating this output at a fixed value using feedback control. So usually this voltage is fixed, but in voltage can be varied depending on application, but always this one is fixed. We want to make a ideal voltage source when you are designing DC to DC converter. So this voltage is always known, and by plugging everything here, so then this is the equation. So this is the equation for the magnitude of this ripple component. Okay, so we fully reconstruct the magnitude component of ripple component, magnitude of ripple component. Initially we ignored everything, so this one was assumed 0, but now we construct that based on the simplified analysis using the constant R voltage, and we reconstruct this ripple component, and this is the simulation result of this one. So ILT, as here, is increase and decrease triangular waveforms with the minimum, average value of the 4M, and this is the capacitor current simulated, right? So AC component is just reduced by this much and coming here, and during on time period, this voltage increasing. No, not on time period. When this current is positive, this is increasing, and during this time is decreasing. Okay, so we use this formula. We derived this in the previous 2 slides, okay, or previous 1 slide. Then this is the prediction of that equation. We have one solution for the magnitude of this. You have another solution from this exact P-SPI simulation. You can figure out this, okay? And we have another solution, the Fourier analysis and the consideration of attenuation by the second order low-pass filter. At that time, frequency domain analysis, we have this conclusion. So we have 3 different conclusions. Which one is the most accurate? This one, probably. This is the exact simulation. But basically, they are the same. You can take this, or take this. Any one of these will be okay. Right? They are within the less than 10% or something like that of the error bound. So anything can be a correct answer. Okay, and don't pay attention on the exact value of this. Engineering sense, they are the same. All right. So this is about that. Okay. Capacitor. Structure of capacitor is very simple. So you have one layer of metal plate like this, and we have another metal plate like this, and we have lead and lead. Okay. So this is structure of the capacitor, and in between 2 metal plate, you feed in the gap with some material, dielectric material, okay, high permittivity, okay. This is structure of capacitor, but you have lead and we have lead. Maybe this lead have some resistance component, and in addition to that, this is non-ideal material. Because of the non-ideal characteristic of this dielectric material, there is some voltage loss. Suppose you applied this across this V, okay, then capacitor voltage, you apply this through some time varying current, positive or negative, then this capacitor will be decomposed into 2 parts, and VC appears between this plate, okay? Then, what happened? Then, and it has, because of the AC component, it has VACT. We evaluate peak value of this, peak to peak value of this, but in addition to that, there is additional voltage drop. Let me call it VESR. ESR. Okay? So there is a voltage drop, and the current is passing through this ICT. Okay? Then voltage drop. this is due to the capacitance of this capacitor, okay? And DC voltage is stored here with some AC component and this extra voltage drop, okay? So in terms of the circuit, equivalent circuit, we use this one. We use additional resistance. This is capacitance of capacitor. This is RC, is called ESR. ESR is this one, equivalent series resistance of capacitor. All right? So some student or some people, they think this ESR is coming from this lead. That is not true. Even if you remove this lead, so you measure voltage across this, or you use very short lead, still this ESR is there. So this is coming from the I don't know, the exact mechanism of this, but it is inherent to this structure and this dielectric material. So this value is not varying with the length of lead. Okay, this will cause very minor impact on this. So this value is fixed. All right. So usually this value is 0.1 ohm or 0.01 ohm, something like that. All right. For the 400 microfarad electronic capacitor, which is the cheapest capacitor in the world. All right. Okay. This ESR is very important in two senses. One is it critically determines the size of ripple component in output voltage or voltage across the capacitor. There is the output ripple. So output ripple is way larger than previous estimation. Theoretical estimation is nothing compared with this voltage drop across this is much larger than those things. Okay, so this is very important for the estimation of our voltage ripple. And the more important aspect is this combination of this R, C create what? Pole or zero. It creates zero. Okay, because when that frequency, this impedance becomes zero. That means whatever voltage appears here, this voltage division is zero. So output becomes zero. That is the definition of the zero. Okay. So this creates the ESR zero, which critically affect dynamic analysis and control design of all the converters. Okay. So this is the most important value, maybe more important than the capacitance itself. But usually students, they ignore this, and industry people, they have no idea about this. Okay, consequence of this ESR is extremely important. You design the converter, okay, and you have good phase margin, gain margin, it ensures good stability. But if you remove this one, suppose you use the cheap capacitor, very cheap, not this one, CHEAP, okay? Then it has large RC, then you have ESR, which boosts the phase characteristic of everything. The converter predicts stability, okay? Now you change this capacitor for the expensive one, like MLCC or some fancy, with very small ESR or no ESR, very small ESR, negligible ESR, then converter immediately becomes unstable, right? Then you will puzzle, right? What will happen? That should be the dead way, because ESR is gone. ESR 0 is gone. 0 is boosting phase by 90 degrees. That helps to secure the phase margin. Somehow, all of the sudden, phase margin is gone, and converter becomes unstable. It starts oscillation. That is one common mistake the engineers they make. Okay, they made because they think they are using the capacitor with very small ESR. Then that 0 is moving to the higher frequency. Then within the bandwidth, the ESR 0 is nothing. After it appears the loop gain crossover frequency, that phase boosting effect is just waste, nothing, becomes unstable, right? So you should know the presence of this, and you should measure value of this, okay? Usually manufacturer, they don't provide information about this, or they provide inaccurate information. So you should, if you build hardware, you should measure this, okay? There are another pitfall, okay? If you measure this using the LCR meter, what you are getting is just garbage, okay? You should use something else. You should use frequency analyzer to measure this capacitor, RC, and L, parasitic inductance, if it exists, right? We'll cover that topic later. Okay, so for this case, situation is different. IC is this one, okay? But this ripple component, we calculated this one in the previous lecture slide. This one is new. This is a resistance. Then the ripple component caused by this is this IC times what? This RC. This is resistor. So we have this type of sinusoidal AC component, and we have this triangular waveform of AC component, and the total, this VC ripple is summation of these two components. So it's shown here, VC ripple. Now is this plus this one is generated by this capacitor. So this peak value, fluctuation of this is evaluated. As previously we discussed this, we derived the formula for this, and another one is this one. This is a resistance, and this waveform is passing through this, and we have this component obviously. Then we have a triangular shape of this one. So del IC is the same as del IL. So usually this one is much larger than this, 10 times more than that. So we ignore this, and this will dominate the output ripple. So if you have ESR, this analysis we have done previous is gone. It disappears, and usually this ripple component is simply this variation of inductor current times ESR of our capacitor. Reason for that is this. Okay, so this is the case. So we did some analysis here. So this result is useless, is not useless. It is useless in this case, but this method itself is very valuable in some cases. In the other cases, you may use this kind of technique to evaluate ripple component of something. But now for this case, this is overwhelmed by this dominant component, and the output is just this one. Okay, so you have one example here. So this is VESR. This inductor current, AC component of inductor current triangular waveform is passing through this. So this is that triangular waveform of capacitor current times this one is this one. This is perfectly triangular waveforms, and we evaluate this del IL based on the ideal equation, and this AC component of our voltage is approximately this one and approximately this one. This is del IL, which is 1.5. This is RC. Then the prediction is this one, and you compare this prediction with this, they are very close. Okay, just consider the ESR of our capacitor. If you want to have smaller output ripple, just use the capacitor with a small ESR. Okay, but you should know the value of ESR for the dynamic analysis and control design of this. Okay, this is the perfect triangular waveforms, right? But this is something different. Why is that? This shape is not triangular waveforms. Okay, that means the some part of AC component is passing through this. Okay, so because of that, the small component is some resistive component is coming into picture. So this triangular waveforms is little bit distorted because some current component passing through this. Okay, maybe 99% of AC component is passing through this, but some small portion of this AC component is going through this. So this waveform is different. All right. So this is the end of periodic steady state analysis of a buck-converter. It's very easy. Okay. We used piecewise linear analysis with small ripple approximation, and this graphical analysis will provide everything for us. You don't have to calculate practically. You don't need to calculate anything, just to sketch this, right? So graphically, you can analyze every waveforms, okay? Of course, we assume the small ripple approximation other than calculation of ripple component in the output voltage, but the result they are very accurate, okay? So they're same, practically same as the piece-by simulation, all right, okay? So easy, but there are not easy story here, okay? So there is a CCM and DCM operation of this buck converter. CCM means continuous conduction mode, and DCM means discontinuous conduction mode. Some people, some professor, some student, they say something strange. Continuous current mode, something like that. It's not that. Continuous conduction mode, discontinuous conduction mode is the acronym for this one. So CCM and the DCM, okay? So why this thing is happening is because of we are using unidirectional switch, okay? Unidirectional switch means this switch is allowing only one direction of the current path. This is MOSFET. As I said, then there is a diode, body diode. There is a diode. If you don't want this, then you use something else. If you use MOSFET, there is a diode, okay? So when MOSFET is turned on, the conduction channel is built, then current is passing through this, and also current can pass through this, okay? It really doesn't matter, okay? But when this conduction channel is gone, due to the low, this gate source voltage, this is gone, then current cannot pass this, okay? So current only pass this direction, okay? So probably you think the MOSFET is bidirectional switch. It's not true, okay? If channel is formed all the time, it is bidirectional switch, bidirectional current flows are available, but if channel is gone, then this direction is impossible to deliver current, and this diode is only passing current through this from anode to cathode. So both of these are unidirectional switch, okay? And this is diagram, circuit diagram of buck converter. So I repeat this, okay? And IL bar, this bar means average version of this IL, I sub L is IO, because this current is 0, average value of this capacitor current is 0, then this is fixed and this is current, okay? Then during on-time period, assume duty ratio is fixed, then this VL is this voltage, this is VS, and this is VO here, okay? So start from here, right? So with some value, this average value is this one, VO. If D is fixed, then output voltage is fixed. Now Vx and R are fixed. Then this on-time slope is Vs minus Vo divided by L. Off-time slope is minus Vo divided by L. And the average value of this waveform is load current IO. So IO is Vo divided by R. IO is VO divided by R. This one is okay. All right. Now you are increasing this resistance R. So R is increasing. If R is increased, then average value of this inductor current will be decreasing gradually. If we increase R gradually, it gradually goes down like this, and there are some instant. This one, this is a very critical instant. In this instant, it starts from 0 and goes to the peak value and go back to the 0, go to the peak value and repeat this. Okay. Condition for this is REL. Average value of this inductor current is exactly same as after 1 second of del IL. Okay. Then you have this situation, right? What will happen if you further increase the load resistance? If it follows this operational principle, then suppose it keeps the previous trend, then it will be something like that. Okay. This is impossible. Why is that? Because in this period, this current becomes negative. Right? This negative current cannot pass through this. Cannot pass through this. Right? Cannot pass through this because this channel is disappeared at that time moment. So this is not true. This is impossible. This is impossible. Let me put X here. Okay. Then actually what will happen is shown here. All right. So it increases this. It is same as this one. It starts from 0 and reach the peak value and decrease it to the 0 and increase like that. Okay. You further increase the R, then this R. Then you will have this and this. Reason for this is, or the only justification for this is output is increased in proportion to the R. Okay? This must be true, right? In this operation, output is fixed. Okay? That means VO is fixed at I'm sorry, this should be D. Okay? So of course D is fixed, right? If this is true, then this on-time slope is Vs minus VO divided L, and uptime slope is minus VO divided by L, right? So this is the slope, right? If output voltage increased, if you increase R further, then this remains the same, but this is increased, then this slope becomes smaller, and this slope becomes more gradual like that. Okay? So this is true. When this R voltage is increased in proportion to R, then this slope becomes steeper, and then this is the correct waveforms. All right? Then what will happen? If R is decreased below the value that established these waveforms, then it will do like this. Then this inductor voltage will be stopped here. That means diode is turned off. Once the diode turned off, it remains turned off. If diode turns on, then the circuit will be shorted, something like that. So once it turned off, it remains turned off for the remaining part of switching period. This is called discontinuous conduction mode because inductor current becomes discontinuous during this period. This is the DCM, discontinuous mode operation. If you increase R further, this area is increasing. Okay, so this DCM period is increasing. So this is the waveform for the DCM operation. Okay, here inductor current in DCM, I copied these waveforms. Here, the same waveforms, okay, and the same circuit diagram. And reason for this is VO is proportional to, of course, D. VO is increased by D, and it also increased by R. If R increased, then output is increased. Okay. So in DCM operation, our voltage increase in proportion to the load resistance, even if the duty ratio remains the same. This is the situation. Duty ratio is the same. All right. A larger load resistance decreases the ascending slope of on-time inductor current. Because this is increased, then this slope will be decreased. So first one is our voltage is proportional to this R, and SON is on-time slope is Vs minus VO divided R, reduces, becomes smaller as R increase. Okay, always, of course, always output voltage is smaller than input voltage. This is buck converter because we are filtering this input voltage, rectangular waveforms formed from the input voltage, so output voltage must be always smaller than input voltage. But this is true regardless of operational mode, and S of time period is minus VO divided by L. Okay, this one increase. It increases in negative direction. So as R increase, this width, this length of this period in which the inductor current is absent, increase. DCM period is increasing. So rather the resistance widens the period at which the inductor current is absent. All right. So you understand this. Okay. This is a PSIM simulation example. Maybe sometime next week or next week, I'll show one demonstration of using this. Okay. This is a PSIM file. This is parameter sweep option. So if you add this, there is the option to change one or multiple of circuit component, probably one circuit parameter. Here we are changing this arrow, and the start value is 5 and the final value is 11, and the increase step is this one. Parameter to be swept is this one, arrow. Okay, so don't type arrow here, you should type arrow here. Arrow, same thing. Okay, arrow is changing from 5 to 11 by step of 1 ohm. Okay, and this is PWM part. So lamp height is 3.8. So lamp waveforms looks like this. And this voltage, this is some fixed voltage. This is unique gain buffer. So this magnitude of this is, this peak value is this one, and magnitude of this is 1.9. And during this period of time, switch is turned on, turned off, something like that. Okay, D. This should be half of this, because this is 3.8, this is 1.9. So this line should pass in the middle of this triangular part. This is long. Okay, so D is this one. You know this, right? So this is 50 kilohertz switching frequency, and period is 20 microsec, and this is 10 microsec. This one. Then this is 0.5. Our voltage VO is VS is 0.5 times this input voltage 16. So this should be 8. Okay. But this is true only in CCM. CCM. So you are increasing R from 5 to 11. So this is the case of 5, 6, 7. They are all in CCM. How do you know that? Because the minimum value of inductor current is larger than 0, okay? More positive than 0. That means for these 3 cases, this is the CCM case, and this one with this value 8 is borderline between CCM and DCM with this value. Okay, this is the 8 ohm. So with this, CCM and DCM. After that, these 3 things are what? This is the DCM. If you increase this gradually, the current absent period is increasing. First one is this one, second one is this, third one is this. Okay, our voltage. Let's take a look at our voltage. This is the case for the CCM. Our voltage is fixed at 6 volt. Okay, and the borderline between CCM and DCM can be considered either CCM or DCM. So it is considered as CCM. So for this voltage is 8 fixed here. But if you increase R further, then voltage is increasing 9, 10, 11. Okay, so this is illustration of the operational mode change. And this file is contained your zip file, so named as CCM and DCM transition, maybe in the folder named topic 01. Okay, use that, try to reproduce this later on. Okay, then you can feel the difference between CCM and DCM. All right, so this is called the DCM. And this operational mode where the inductor current is present all the time with positive value or 0 value like that. This is called CCM, continuous conduction mode, and this is the DCM. DCM it stands for discontinuous conduction mode. Okay. Why this happened? Then because of you are using unidirectional switches, MOSFET and diode, that is the reason. To avoid this, you can use MOSFET here, which is operating in complementary fashion. When this thing is turned on, this switch is turned off, then it works as the pair of MOSFET and diode. When this is turned off, this MOSFET switch is turned on, then it works as the diode turn on time of this conventional mode. Then this DCM operation is gone. Okay, so if you use 2 MOSFET switches, they work in complementary manner. So they call it synchronous buck converter. But they are not synchronized. They are asynchronized. Okay, complementary fashion, maybe asynchronized reactive the buck. Okay, but they call it just the synchronized. There is just some timing exchange between them, so they call it synchronized buck. This can improve the efficiency of this converter because if the high current passing through this loss power loss is significant sometimes. Because of this works as the finite voltage source, and this works as resistance, small resistance. Okay, we just concentrate this conventional one. Then why DCM is important? Because you design your converter in CCM. You want my converter would remain in CCM all the time, but that is impossible. Okay? There is a many operational mode. Load resistance can be increased, okay, or some energy saving operational mode that the load current becomes very small. Then converter inevitably goes into DCM operation. So you cannot avoid the DCM operation, okay? So you should consider this, you should understand this DCM operation as well as CCM operation. So we'll spend some time on this topic. Condition for the DCM of something, okay? This is a borderline. This is borderline between CCM and the DCM operation. For this borderline, condition is this average value of this one is half to del IL, okay? If IL increase, it goes into CCM. That means R is decreased, then it goes into CCM. If R is increased, the average value of the R is decreased, then it goes into this DCM operation somehow like this, okay? So borderline between there is very obvious. When average current is larger than this one, larger than this is the borderline. If average value is larger than this, then this becomes the CCM, okay? So condition is this one, and the IL is average value of current, which is the same as average value of inductor current, which is this. And the del IL is this one. This is uptime slope, uptime period. I said always try to use our voltage when you are calculating something, all right? So if this condition is met, you are in CCM. Otherwise, you are in DCM, okay? If you have equal sign, you are in borderline, okay? So borderline is this condition. Borderline condition is this. And if this you have this sign, this is CCM. You have this sign, this is DCM. Okay? So borderline condition, let's denote that resistance, load resistance, which puts this converter on the borderline between CCM, DCM, is called R critical. So this one is average value of inductor current. It's same as the half to this del IL, which is this, okay? And from this equation, you find out the R critical, which one is this, and from this, you calculate again from this equation, you calculate L critical. If R is larger than R critical, you are increasing R, you are decreasing the average current, average value of inductor current, then this is very easy, okay? It will go to the DCM, all right? If you decrease the L, smaller than L critical, it goes to the DCM. It's not easy to see compared to the previous one, okay? Let me give one example here. So this is the borderline between CCM and the DCM, and you increase your inductance further, that means this slope is increasing like that. You should have this kind of waveforms, which is impossible. Okay? L is smaller than L critical. This is L critical. Right? This IL, IL prime. Okay? So with this, you can understand the inductor is smaller than L critical. The converter confront with DCM operation. All right? This is opposite to that with this. Okay, we stop here, and for the first day, we finish up the remaining part of the DCM, and we'll move into the closed loop operation of this. Okay? All right, thank you.